So in the last video, we defined the electric field and then wrote down an expression for the electric field for a simple point charge in space. And if you remember, we talked about physical and analytical models. The physical model would basically look like this, where we have a point charge that's just somewhere in space. It's indicated here by the letter Q with the plus sign, indicating that this is a positive point charge. And the electric field is emanating from the center of that point charge in all positions. And with the definition of the electric field, what this basically means is that if we were to put this test charge, represented by Q naught, it's going to experience a force. Wherever we place that test charge, outside of the center of the point itself, it's going to experience a charge indicated by these little force arrows that are always going to be pointing away from the source charge. And that's exactly what the analytical expression is showing here as well. So again, this is the definition, but this is the electric field from a point charge. This is the expression. This is the analytical model. And we put the constants, we described the vector, and then what we did was we just walked through a simple calculation of the magnitude. So what we said was, let's not worry about the vector characteristics. So these bars here indicate that we're dropping any consideration of the vector nature and where it's pointed, and we only want to consider the magnitude. So for a charge of 1 coulomb and a radius of 1 meter, we can put those values into that analytical expression, and after some time, carrying the units through and everything, we come up to this expression for the magnitude. And I just realized that I to be consistent, I should have that vector arrow showing here. So the magnitude of the electric field is what we ended up doing. So another point that I really want to emphasize here, we took some time to go through the units. We carried the units through. I never really made it clear that this expression only works if we use the appropriate units. And when we plugged the 1 meter into this equation, it was implicit. It's very, I chose to use 1 meter because it was convenient. But the choice of that unit of meter is extremely important, because this expression only holds up if we use the appropriate units. And those units are referred to for this expression as SI units. So I'll just write it down, and I'll try to leave references to read up on these units. There's plenty of articles you can find on open source like Wikipedia. So this is really important, because what that means is that we have to enter numbers into the expression that conform to these units. So if I ask you to recalculate this expression, but let's say that I was asking you to do it for R equals 1 millimeter instead. Well, let's go ahead and calculate it out. So give myself a little bit more space here. We see the expression. So let's just say E. I'll go ahead and put it in explicitly. I'm going to say magnitude, again, of the electric field for R equals 1 millimeter. It's a pretty large expression there, but I'm being very clear that we're going to do the magnitude of the electric field at 1 millimeter. So let's write this out. We're going to drop the vector signs. We're going to go ahead and say Q. Let's put that in explicitly. We're going to say 1 coulomb, and it's divided by this 4 pi epsilon naught for our constant. And then we're going to put in brackets here R equal to 1 millimeter. And we're going to square that. So when we remove these equal signs and replace them with actual values, you'll see here's where it can really get tricky. So let's not worry about the constant for now. Actually, what I can do is I'll keep bringing this along, but I'll say this Q equal to 1 coulomb divided by 4 pi epsilon naught. We actually worked that out already. And I'm skipping a little bit of the discussion on the units here, but I know that if I just take 1 coulomb divided by that value for the constant, then I'm gonna get this value of 8.988. We'll go ahead and keep the 3 digits for now. Times 10 to the 9th, but it's not volts per meters because we haven't. We're going to keep the distance out of the calculation for now. So the units here are actually going to be volt meters because I'm going to multiply. So let's just go ahead and put this in parentheses. That's the units for that constant. And just to reiterate, 1 coulomb divided by this number, which also has the units for epsilon naught that we represented up here. So you can work that out yourself and see that it actually comes out to that number. And I'm going to go ahead and carry, so here's the 1 over r squared. So this is going to make this little exercise a little bit simpler. So we can always come back to that number. So what I really want to focus on right now is this 1 over r squared. So if I just repeat that here, and you know what, let's just go ahead and I'll even reduce this, make it even simpler. I'll just round it up. Let's just call it 9 E9. And some of you guys in class had actually, brought this up. So we'll go ahead and say 9E9 is as a single constant, volts per meter. And now this is divided by r squared. So let me make a little more room. And we know that we want to make sure that this is in meters and not millimeters. So let me just put the brackets so we don't forget. This is going to be something that we're squaring. So I'll just leave it here. And what I need is a conversion. I know that I need this unit to be in meters, but I'm asking you to do it in meters. So what is that? Let's just go off on the side here. That's probably as good as any. So if I know that 1 millimeter equals 0.001 meter, then that is a conversion factor. So I'm going to take my millimeters, and you can just use basic algebra to get it in the form of what meters would be. So what I can say is 1 millimeter is equal to that. Well, if I divide, let's say I had 1 millimeter here. If I can put a conversion factor in here such that my millimeters is in the denominator, then I will be able to cancel out my millimeters. So I want to take this 1-to-1 conversion table and basically get this so that millimeters is in the denominator. So one way I can do that is by dividing both of these sides by 1 millimeter. And we learned this, a long time ago, that whenever we divide quantity by itself, as long as it's not 0, we'll get 1. So I end up with this number 1 is equal to 0.001 meters divided by 1 millimeter. It's the exact same thing. So this quantity here would be something that I'm going to look up on the internet or pull from a conversion table, right? And all I did was apply some algebra to it to get it into this form, because what I want to do ultimately, if I can multiply this by 1, you'll see what happens here. Let's continue this on. I'll go back to black in this case, and I'll need more space again. So I'll say 9E9 volt meter, and let me just make this larger so we can really see what is about to happen. I'll make my bracket. I keep going back and forth between bracket and parentheses, but hopefully that's not causing any confusion. And I have 1 millimeter and I want 1 millimeter to actually read in meters. So what I'm going to do is multiply this by 1. So I'm going to go ahead and put a multiplication sign here. And I'm going to add another bracket in here. And this is going to be my unit conversion. So 1 is equal to 0.001 meters over 1 millimeter. So let's just write that down. 0.001 meters divided by 1 millimeter. And remember to keep track of the brackets. We didn't do the squaring yet, and that's really the most, probably one of the most important things here. So what can I do now? I know that this is equivalent of something being in a numerator, even though I don't show it. I could just as easily put a line that has that divided by 1. So I've got 1 millimeter divided by 1 times 0.001 meter divided by 1 millimeter. We know that these units are going to cancel, millimeter and millimeter. And what I'm left with is one meter. So let's keep writing this out. I'll just bring it down here now. 9E9 volt meters. And then in the denominator, if you look at everything that we've canceled out, this is just going to be a 1. We're not going to worry about the 1 in the denominator anymore because those units have canceled out. So it's 0.001. Squared. And as I continue along, I can separate the units from the numbers, as we've done before. So zero point 0.001 squared, and don't forget my unit, meter squared. So I've appropriately accounted for squaring the number as well as the unit. And now you can see here we're going to get another cancellation of units. So I can say 9E9 volts meter, or I should, yeah, well, let's just write it out. Let's do the squaring here. 0.001 squared is the same as 1 times 10 to the negative 3 squared. So it's going to be 1 times 10 to the negative 6, because 3 times 2 is 6. And that was meter squared. But we cancel the meters up top. So now you might be tempted to reach for the calculator, but this, intimidating looking, calculation is probably not as bad as you might think. So one thing, let's rewrite this. Let's separate the units. So our units, I want to separate the units from the numbers. So we ended up with volts per meter. So let's just go ahead and we usually put that at the end. So I'll just go ahead and say we know that it's going to be a number multiplied by volts per meter. So let's find the number that we put in here. And that's really the source of this calculation. So we've got 9E9 divided by 1 times 10 to the negative 6. Well, 9E9 in scientific notation is 9 times 10 to the 9. And instead of saying 1 divided by 1 times 10 to the negative 6, you might remember that that expression looks like a y, but it should be in multiplication, is equivalent to 1 times 10 to the positive 6, right? So what I can do is replace this, so that's 1 times 10 to the positive 6. So now you remember from multiplying exponents, 9 times 1 is going to be 9. And all I have to do now is add these exponents. So it really wasn't all that bad. So if I add if I add 6 to 9, I'm going to get 9 times 10 to the 15 volts per meter. So if I can just clean this up, if we compare what we did with the previous calculation, so this was the magnitude of E for, we still had one coulomb, and let's say R equals 1 millimeter. So those are the values that we used for this calculation. And remember to the calculation that we did up here, where all we changed was the distance. And aside from the fact that we rounded up just to the first value to the left of the decimal point, the most striking thing that you'll see is that the magnitude between these numbers is so enormous. We've gone from 10 to the 9 volts per meter, on the order of 10 to the 9, all the way up to 10 to the 15. So it's 6 orders of magnitude. It's multiples of 10 to the 6 in exponent, which is really an enormous swing. And you might be thinking, well, is something wrong with that calculation? And it's not. This is the behavior. This is the relationship that you see using our expression. And the issue is that this denominator, this 1 over r squared behavior, is going to give you extremely large values the closer you get to 0 without ever hitting 0, because this expression doesn't allow us to calculate 0. So it pertains to the field for locations outside of the domain of r equals 0, often to infinity. But as you get close to that small number, closer and closer to 0, that number really starts to explode because of that exponent in the denominator. And the same can be said for looking at distances that are very far away. So as you start to approach infinity in r, you can see how this number is going to get smaller and smaller, and eventually it approaches 0. So that's consistent with these two calculations. 1 meter is fairly far away, relatively speaking, to the 1 millimeter. And you can see the behavior here is going from extremely large values at close up to extremely small values at further away. And this sets us up for our next discussion of looking at trends over large spreads of values. So we're gonna plot this at various distances coming up to see if we can get a better feel for what the behavior looks like.